Hey everybody, Jason Hollern from EPRI. Excited to be here today. Thank you all for attending. I'm going to talk a little bit about cyber physical digital twins, get into those, and then we'll talk a little bit of how those can be augmented and modified to really start taking into account some of the cybersecurity aspects and functions of detection. So first, I'm not going to read any of this, but what I will do is I'll let you read it, and then if you want to connect with me, feel free to scan the QR code. I promise I won't give you up or let you down with that. So feel free to go ahead and connect with me on LinkedIn. But what I will use this slide for is to talk a little bit about EPRI, because I don't have a background slide on EPRI, and really what we do is very critical for the electric power world. And EPRI is a 501c3. We're a nonprofit, so we do not lobby. We don't recommend any one product over another. We are a fact science-based organization and do a lot of research a year, working with over 435 electric utilities from around the world. And part of that research that we do is dedicated towards cybersecurity for transmission, distribution, behind the meter assets, non-nuclear generation, renewables, hydro, and then of course we have a nuclear cybersecurity effort as well. So with that in mind, what you'll hear today from me is a non-commercial technical talk, but I'm going to keep it up a little higher level because there may not be folks in here that are engineering minded, more on the policy side, as kind of what this conference is really geared towards as well. So with that, how many people know what a digital twin is? Yeah, a couple. How many different types of digital twins are there? So there, when I say digital twin, do you know what I'm really talking about? And the answer is it could be yes, but it could be one or another, because it's one of those terms that's quite ambiguous, right? So when some people think of the word digital twin, they may be thinking about a visual digital twin, like a visual 3D representation of an asset, a piece of equipment, a plant, a building that can then be zoomed in and see some sort of aspect associated with that. And some folks call that a digital twin, and rightly so, right? Because it is a visual representation that is represented digitally compared to the physical asset. Now, when we talk about data associated with those, there are some aspects of data that can be flowed into those types of digital twins, mainly in the form of like overlays. So like if you want to see an actual visual representation, but then overlay operational data, for example, like operating pressures, power levels, temperatures, those can all be used as a visual aid for people that are working in the field. They can be used for helping with designs of new systems, so on and so forth, right? The other type of digital twin typically doesn't have an actual visual representation associated with it, and it is a first principles digital twin. So first principles of what I'm really talking about here is mathematics equations that are physics-based, that are used to actually develop a set of equations, fast Fourier transforms, that physically model the process that is occurring inside of that piece of equipment. So for example, if you have a pump and you want to understand how that pump operates from a physics standpoint, you need to understand and know what the pump head is. You need to know what the pump bore size is, what your impeller size is, the shape of the impellers. And those can all be modeled empirically through equations, physics equations, mechanical engineering equations. and put into a computer program. That is a first principles digital twin. And it uses those first principles, which are ground truths, to actually model physically what is happening inside that piece of equipment. Now, in the data analysis world, the AI world, we use both of these types of digital twins, but the first principles digital twin gives us the ability to expand upon some aspects of operations, maintenance, and eventually what we're hoping is cybersecurity, right? By bringing in actual data and incorporating that together with these first principles digital twins. So when we build out a digital twin at EPRI, what does that actually look like? Well, on one layer, we bring in, like I mentioned, data from that asset, of how that asset actually operates. So that's typically like historian data, right? So you have a control system. That control system has a historian associated with it where it's scanning and recording multiple points from sensors and transmitters that are out in the field. That helps to provide a historical database that then can be brought in, and we use that to help fine tune these digital twins, right? Because if we're doing something very complicated, let's say we're actually developing a digital twin of a gas turbine, like a jet engine. Well, those jet engines come off an assembly line when they're being made, but there's differences in machining tolerances. There's differences in, specifications. Each physical piece of equipment that's made is not 100% identical to the one that comes off next. So we can use the historical data to help us fine tune that model, to help make, instead of a generic digital twin of a particular make and model of jet engine, we can then make that a very specific model to that particular jet engine that you have hanging off of your airplane wing. So that helps us fine tune it. Then we can bring in additional data, like weather data. We can bring in outside data, like other historical databases that may have been used, for example, the maintenance history associated with that. Because when you start bringing in these other data, it can give you additional insight into how that piece of equipment has been run historically, what maintenance might have been done that can impact its life cycle, and also its degradation over time. So you can help build out a different view of what's actually being done with that piece of equipment. And then the next layer is those physics-based equations that I had just mentioned. And then finally, we get into what you actually want to do with that digital twin. What is that digital twin's purpose? So that's where the calculational layers and the output layers of how you're going to actually use that data comes out of this piece of software actually occur. Okay, so when we build a digital twin, what do we need to do? This is a very high level process map of building out the digital twin and what we're going to be doing for building out an attack library. So we start with a base model of a first principles digital twin, and then we'll start bringing in new data to that to help build the context associated with cybersecurity. So what do we want to bring in? Well, we need to bring in things like control layers that typically aren't modeled in a digital twin. We need to bring in communication layers that typically aren't modeled in a digital twin. We need to start associating that with attack libraries. So we need to build out attack libraries that can give us some insight into what an attack might look like according to the impact. And we'll talk a little bit more about that on the next couple of slides. Then we need to actually do some physical testing, right? Because that's where the tuning comes in. When we start putting all these equations together, we start looking at the output based on those calculations. We need to actually compare that to the actual piece of physical equipment that we're modeling. Understand how that piece of equipment actually operates in the real world, what its responses are to certain inputs. And then we can use that to help fine tune the actual model itself to make sure that our model is more accurate. And that's kind of a continuous cycle in itself. And then it all starts over again as you start wanting to add additional capability to your digital twin models. So let's take a gas turbine and look at that. Just by a show of hands, how many gas turbine experts do we have here? Yeah, right. So we'll just quickly go over this and talk about that. That's okay. I'm not a gas turbine expert either, right? So that's why I really put this up here. But here's some really interesting parameters that that you can kind of look at, because this is what we're modeling. We're modeling a gas turbine. Basic pieces and parts of a gas turbine are your compressor, your combustor, and your turbine. And those, your compressor and your turbine are connected by a single shaft that also connects to a large generator. And what I'm really talking about here is not just like a jet engine on an airplane, but something that is going to create electricity that electric utilities use every single day to produce electricity for their customers. And with that, these, depending on where you are in the world, and if your country runs on 50 hertz or 60 hertz, your gas turbine only runs at 3,000 RPM or 3,600 RPM. That's it. So they're not spinning incredibly fast like a turbocharger, you would think, right? Or other pieces of equipment. They put out between 150 and 300 megawatts typically. But if they're attached to other pieces of equipment, like in a combined cycle plant, like a heat recovery steam generator, where the exhaust that comes out of that turbine section is used to actually boil water in tubes, and then that goes to another steam turbine versus a gas turbine, and combined with some others, you can start getting some real increases in efficiency in this technology that then provide a lot more electrical output. So these things can get very complicated very quickly. So when we start looking at building the actual digital twin models out, we typically do that in bite-sized pieces, where we'll model the digital twin of the gas turbine itself, then we'll model the other pieces and parts and kind of put them together. So when we're building this out, this is kind of where we start with those physical models. We'll have a model for the compressor, what the compressor is doing, and a model for the combustor and what the combustor is doing, and the turbine. And those get all put together to become this digital twin model. Now, looking at and understanding how these pieces of equipment fail is another piece, right? Because when we start talking about cyber attacks, a lot of those cyber attacks may simply look like regular equipment failures, right? To where if you change your coil or your register or a set point in the DCS, a piece of that equipment as part of that gas turbine may not function like it's supposed to, or what we totally expect. So we kind of break this down to understand the major failure modes associated with some of these pieces and parts associated with the gas turbine itself. So here you have, a listing of compressor, combustor, turbine, and then different types of ways that each one of those could fail and the impact associated with those failures. Well, those failures, again, just to kind of repeat, can easily be thought of as cyber attack, where an attacker changes something in the logic, and then that logic is played out through the control system, and it looks like a failure of one of these specific pieces of the turbine itself. So if we're going to do this for the digital twin, we're going to build out this digital twin and we're going to have it for cybersecurity, we need to do some things. we need to specifically take those base models. We need to bring in additional data sets, as I mentioned, and we need to understand what types of attacks may occur on the system that we would like to get early warning for to help us with the detection function of a cybersecurity program. Because if we're able to detect this type of activity through modeling and bringing in that actual live data of how the physical system is actually running its communications and what's happening in the DCS, we can try to detect anomalous activity sooner and potentially reduce the dwell time that an adversary is actually in our DCS networks or OT networks. So there's a lot of things there that we can kind of look at. Some of the things that we would want to monitor, like what are the HMI views that are being presented in the control room itself versus what's actually being stored in the historian. Those are, we start running through those impacts and work our way backwards, which I'll show here how we actually are planning to model those using the MITRE ATT&CK framework for ICS. But it'll help to drive the types of data that we're actually going to need to bring in, right? So we may get through this and say, hey, there's these 5 different new attacks that we would like to get data on for detection. That may drive additional data sets that we need to go find, or we need to develop through monitoring, or need to develop and bring in that we may not have thought of early in the process. So one of the really hard parts of this project is actually modeling the control and communication layers. To my knowledge, this really hasn't been done for the purpose of a digital twin yet, and we're kind of breaking new ground here. So when we look at it from a physical asset point of view, we can do some physical testing on those physical assets to really start understanding what those impacts would be. So we have the physical asset layers, and we have the network and communication layers, and part of that is this DCS piece that's built into the network and computational piece. On the next slide, I'll show you what some of these control loops look like. But really what we can do is we can start to look at what some of the outputs are and what the impacts are from doing some physical testing in the lab. And I'll also talk about that here in another minute. But the biggest hurdle to overcome here is effectively modeling that, especially from a first principles standpoint, and building that into a first principles type model. So where that translation takes place is actually not a trivial concept to kind of get over, and also to build out. So when we talk about the different types of loops, we're really talking about different types of logic that takes place within these DCS systems. And you have a protection logic that's there really to help protect and maintain the integrity of the system. Those are helped with startups and shutdowns to make sure that you're not actually going out of parameters and causing equipment damage. Could also be looking at other types of other protection mechanisms, like how much ammonia may be being used in the process, or other type of chemical injection, so that you're not releasing anything to the environment that shouldn't be released. You're staying within specifications. And then you have over on the other side your continuous logic, which really has 5 different control loops associated with it. And within those 5 loops, you have one for temperature, speed, and acceleration, right? To keep your operating parameters within certain boundaries. And then you have a manual and a startup loop, and those those are used to, again, help your operators start up the machine, shut it down, and then also cause a good transient so it can go from one power level to another power level, providing, additional heat rate and increasing efficiency as it goes up. Now, if something deviates from any of these, it could automatically shift from one mode to another. It could put you into, let's say you are outside normal temperature boundaries for too long, cause an alarm and automatically push you down to a manual state. It could also go into a shutdown state. You can possibly trick the control system by feeding data to it to say, hey, it looks like I'm actually starting up. Let's move to a startup state and possibly cause damage to the machine itself. So there's a lot of things that we can kind of model in these these actual control loops. And we'll be trying to actually test some of these in our laboratory to help fine tune these models. All right, so when we start building out our attack library, typically what you would do is start on the left and move to the right in this MITRE attack for ICS framework. Here within the context of this effort, we have to make some assumptions, right? Because when we're looking at starting on the left and moving to the right, we're looking at how an attacker is going to gain initial access in the system, how they're going to work their way down into lower levels, how they're going to move laterally left and right in the system, how they're going to understand what that system actually is that they're in. But for the context of actually building out this model, we're really concerned with the impact, and that impact's all the way on the far right. And in order for us to build out that attack library and cause an impact to a physical system so we can help use that data and provide those attack scenarios and the outputs that are associated with that attack, really what the machine is doing in real time when this attack occurs, we need to start all the way on the right and then work our way backwards. So we want to cause an impact in the lab, right? So we are going to attack physical systems to see what actually happens. And that data, again, will be used to help fine tune the model so that we can build this attack library so that when it's seen in the model, it can actually be alerted on, detected, and say, hey, this could possibly be some sort of anomalous activity or a cyber attack. Now, what that looks like is, let's say we're going to build out an attack that is manipulation of control. We would typically say, okay, we want to cause this manipulation of control. How are we going to do that? Well, we would really need to modify the control logic. Okay, so if we modify the control logic, again, working backwards, what can we do to inhibit the response function associated with the actual DCS system? We're going to, again, modify that control logic. How would we do that? Well, we would maybe, modify the coils or the registers associated with the Modbus protocol that is being used within that DCS system in the controls network communication. We'll use Metasploit to build out an exploit to actually do that. So that's an example. Looking at command and control and collection, we would need to know some information to actually pull off that exploit. So that's where some of these assumptions are going to come in. We're going to have to make some assumptions that the attacker is already down in that control level. They have some background information that they've been able to obtain. And that background information will need to be used within the exploit so that we can actually cause that impact to the physical system. So that's kind of how we're actually developing the method to get those impact examples out and then help tune the digital twin model to improve accuracy. Okay, so let's say we've got this model built. There's two ways that we're going to be doing this. Number one, the first step is lab. We'll build this out on a lab level. And what that'll do is that will help us to, again, make sure that the process that we're using for building these digital twins for cybersecurity is done using a good scientific method. It's scalable, it's repeatable, and it can be rolled out to industry. So the very first step is to model a simple flow loop. So we have a flow loop in our Charlotte EPRI cyber and INC lab, where we literally flow water in a circle from one tank to another and back again. But it's really representative of an actual physical OT system because it's made up of pumps, motors, valves, digital valve controllers, heaters, tanks with a ton of instrumentation associated with it. And there's multiple DCS systems that can be used to control this flow loop. On top of that, there's multiple cybersecurity OT systems that and products that can be used to generate additional security level data that can be used to push into the model itself, the digital twin model itself. So step one, build the model for a simple system like the flow loop. Physically attack the flow loop with malware, with cybersecurity operations, and collect the output of that to then fine-tune the digital twin model to prove the scientific method and get critical feedback on that process before we go and modify base models for the gas turbines. Step two is to take the standard models that have already been developed for digital twins for gas turbines that are being used for things like on that other slide, smart dispatch, equipment maintenance, and equipment health, day ahead modeling, trading, and then start building in some of these cybersecurity layers to that using the same process so that we can scale from a flow loop type model to an actual physical asset that's installed at utility and running. How are we going to do that? Well, again, taking the laboratory that we have and building out the attack library in the lab, but then going to actual site. And with this, we will be going to Plant Berry, which is near Mobile, Alabama. It's a Southern Company site where they have several combined cycle units, but they have a high fidelity simulator. And of course, we're not going to be able to run cyber attacks on a real operating piece of equipment like a combined cycle unit that they have there. But using the high fidelity simulator, we will be able to simulate those attacks on that simulator to determine what those outputs are going to look like from that physical machine that's on site. And that'll give us that feedback. We'll take that feedback, incorporate it into the model. And then the nice thing is to accelerate this, there's a commercialization plan associated with it. So this isn't just a theoretical academic exercise of building this tool. It's what do we need to do to take these to the next steps to actually get OEMs, third parties, vendors, all the above, to take the technology and start implementing it so that it's available widely for the industry, right? So the acceleration on that part is just as important as the research and the development of the tool itself. So with that, I think I've maybe time for a question or two.
How big is that? I'm an attacker, a digital twin is.
Yeah, great question. Yeah, great question. So I'll repeat it for folks online. The question was, if I have a digital twin, I obviously need to protect that digital twin too, because if that digital twin is exfiltrated, it gets into the hands of an attacker, you're basically giving them a playbook, right? Because you are giving them you're giving them a leg up. When attackers get into a network, it takes a long time for them to understand where they are, right? Because they may land, they go down through a jump host, land on an engineering workstation, right? And then it'll take them a while to figure out, what type of piece of IT equipment that they're on. And then it take a long time to like enumerate that network. Well, if you give them a digital twin, you've given them basically kind of the Cliff's Notes of that network and what that looks like, especially when you start building in the DCS and communication layers that typically aren't there for a real digital twin. So the digital twin itself is a model that needs to be protected. EPRI has actually done additional research on how do you protect AI, because this is AI, right? This is machine learning, the perfect examples of machine learning. So there are things that you need to do, like keep it on secure networks, right? You don't want to keep this thing out there in an IT network that's accessible by anybody in the company. So it's going to be, on secure networks, you're going to have to secure your data, because as you saw in the slide, a hybrid digital twin is getting real-time data in, right, from various disparate data sources, whether those are IT networks, your OT security monitoring system, your historian, everything, right? So you have to secure that data as well. So when you kind of look at it, we've talked secure by design, those concepts go into, developing out the digital twin model itself, but also how you implement the model in your network. So you need to kind of take a step back and say, okay, if I have this tool, it's high risk, it's high security tool. What do I need to do to my network to protect it? Any other questions? Yes, sir.
Hi, Dominic Berry. So
yeah,
and that's very dangerous.
Sure.
But getting a lab environment set up that replicates production environment can be expensive, at least. That's an area that digital twins, by patches in a digital twin, production environment.
Yeah. So the for folks online, the question was, could a digital twin be used to possibly model your environment to do patch regression testing, prior to actually doing that patching cycle? I think eventually, right? So the first iteration of this will be for detection. Once you model out your communication layer and your DCS layers or your control layers, you may be able to look to see, as I apply the patch and I start doing some normal communications on the network, how have things changed, right? So use that tool to say, before I changed my logic, before I put the patch on, I have my baseline. What's different from my baseline now? And then say, okay, is that acceptable? Is that not acceptable? I think one of the great advantages of working with, the major OEMs of the control systems is that they do a ton of testing before they release any of those patches. So a lot of that responsibility can kind of go back to those OEMs, but it's not to say 100% of the time you don't want to be looking to see what those impacts are of applying patches before you actually do it, especially where maybe the patch is applied to a non-DCS piece of equipment.
So much.
Yeah, thank you.